class we have studied about indifference. We had discussed this formula. Condition for bright band is path difference is equal to n lambda. Condition for dark fringe or dark band is path difference is 2n plus 1 into lambda by 2. Position of all bright bands from the center is y equal to dn lambda by d. Position of all dark bands from the center is y equal to n plus 1 into d lambda by 2d. Then bandwidth, linear bandwidth of all bright bands and dark bands, beta equal to d lambda divided by d. Okay, so these much formula we have discussed in the last class, and also we have seen intensity of all bright bands is I equal to 4I0 and intensity of all dark bands is equal to 0. So all bright bands have same intensity 4I0 and all dark bands have same intensity 0. Okay, now we can draw the intensity distribution curve. Intensity distribution curve for indifference. Here the graph is plotted with path difference along the x-axis and intensity along the y-axis. Okay, and we know that the condition for bright band is, what is the condition for bright band? Path difference is equal to n lambda, and the condition for dark band is path difference is equal to 2n plus 1 into lambda by 2. Isn't it? So for 1 lambda, 0, 1 lambda, 2 lambda, 3 lambda, 4 lambda, etc., bright bands are formed. Isn't it, children? Then for 0.5 lambda, 1.5 lambda, 2.5 lambda, etc., dark bands are formed. And also we know that the intensity of all bright bands 4I0 and intensity of all dark bands 0. So using this information we can draw the graph like this. Here the graph is plotted with path difference along the x-axis 0, 1 lambda, 2 lambda, 3 lambda, etc. At the values 0, 1 lambda, 2 lambda, 3 lambda, etc., we know that bright bands are formed. Isn't it? Having what the intensity of all bright band 4I0. So we can draw the graph like this. So these are all bright bands. Okay, these are all bright bands with a maximum intensity 4I0. So here this one, these are all represent bright bands. At 1 lambda, 2 lambda, 3 lambda and 1 lambda, 2 lambda, 3 lambda on the other side, bright bands are formed. So this represent bright band and its intensity is equal to 4I0. And here this value, what is there between 0 and lambda? This is 0.5 lambda. Here it is 1.5 lambda. This is 2.5 lambda, etc. And here also 0.5 lambda on other side. This represents 1.5 lambda and this represents 2.5 lambda, etc. So at 0.5 lambda, 1.5 lambda, 2.5 lambda, etc., what bands are formed? Dark bands are formed. Okay, what is its intensity? Intensity is equal to 0. Okay, so this is the variation of intensity with path difference for bright bands as well as dark bands. Again we can plot the graph between phase difference and intensity. Okay, phase difference and intensity. And we know that if the phase difference is 0, 2 pi, 4 pi, 6 pi, 8 pi, etc., intensity will be maximum. That corresponds to bright band. Isn't it? So condition for bright band is phase difference is 0, 2 pi, 4 pi, 6 pi, etc. And the condition for dark band is phase difference is equal to pi, 3 pi, 5 pi, etc. Okay, so at values 0, 2 pi, 4 pi, 6 pi, etc., intensity will be maximum and its maximum value is 4I0. And at intensity pi, 3 pi, 5 pi, etc., this is pi, this is 3 pi, this represents 5 pi, etc. Here also on the other side pi, here 3 pi, here 5 pi, etc. All other corresponds to dark bands where the intensity is 0, and this corresponds to bright band where the intensity is maximum, which is 4I0. So we can plot the graph between path difference and intensity. We can also plot the graph between phase difference and intensity. Okay, children? We have linear bandwidth of a bright fringe and dark fringe is beta equal to d lambda by d. Now what is the angular bandwidth? We have to just by heart the formula for angular bandwidth. What is angular bandwidth? Just I will explain. Only formula is needed for you. So here this is interference pattern. Here these S1 and S2 represents the coherent source. Here this represents the interference pattern. Okay, alternate bright bands and dark bands. Let this is the central band. The central band subtend an angle at the center, okay, or at the source, original source. The central bright band or any band subtend an angle at the center. So that angle is called the angular bandwidth. So any bright band or dark band, it subtend an angle, that is called the angular bandwidth. Clear, children? So angular bandwidth means here we can write this is the bandwidth. Bandwidth beta equal to d lambda by d. So linear bandwidth is beta. This distance is beta equal to d lambda by d. That subtend an angle at the center. So theta is equal to, here this can be considered as an arc divided by radius. Okay, so theta is equal to beta divided by d. D represents the distance between coherent source and the screen. Okay, children, so theta equal to beta divided by d. So angular bandwidth is theta is equal to beta by d. Beta is d lambda by d, the whole divided by capital D. So angular bandwidth is given by the formula lambda divided by d. Okay, children, so just by heart the formula for angular bandwidth, which is given by lambda by d. Okay. Now we can do some numericals relating interference. First question, laser light of wavelength 630 nanometer incident on a pair of slits produces an interference pattern in which bright fringes are separated by 8.1 millimeter. A second light produces an interference pattern in which the fringes are separated by 7.2 millimeter. Calculate wavelength of the second light. So this is the question. So what are the values given here? For wavelength 630 nanometer, what is the bandwidth? The fringes are separated by 8.1 millimeter, means that represents the fringe width. So fringe width is 8.1 millimeter. For fringe width 7.2 millimeter, we have to calculate the wavelength of the second light used. Okay, so for 630 nanometer, what is the fringe width? 8.1 millimeter. For 7.2 millimeter fringe width, we have to find the wavelength. So these are the values given. So initially lambda 1 is 630 nanometer. We can convert to meter. 630 into 10 raised to minus 9 meter. For that, what is the fringe width? Beta 1, it is 8.1 millimeter. Again it can be converted to meter. 8.1 into 10 raised to minus 3 meter. Okay. Now the second case, beta 2 is given. Beta 2 is 7.2 millimeter. Again it is 7.2 into 10 raised to minus 3 meter. We have to calculate lambda 2. Clear? Now what is the formula for bandwidth? We have fringe width is given by fringe width beta is equal to d lambda divided by d. Fringe width beta is equal to d lambda by d. For beta 1 we have d lambda 1 by d, and for beta 2 we have d lambda 2 divided by d. The values of capital D and small d remains same, because same interference condition is applied for both the cases. Now we have to find out lambda 2, no? So just divide the two equations, beta 1 by beta 2, like this. So we have beta 1 by beta 2 is equal to d lambda 1 by d, the whole divided by d lambda 2 by d. So that is equal to lambda 1 divided by lambda 2. Substitute the values. Beta 1, which is 8.1 into 10 raised to minus 3. Beta 2, 7.2 into 10 raised to minus 3. Lambda 1, which is 630 into 10 raised to minus 9. Lambda 2 we have to find out. So lambda 2 we can simplify as, after simplification, lambda 2 equal to, this can be cancelled, lambda 10 raised to minus 3 and 10 raised to minus 3 get cancelled, and after simplification we will get 560 into 10 raised to minus 9 meter or 560 nanometer. So wavelength of the second light is 560 nanometer. Okay. Second question, in Young's double slit experiment, lights of green, yellow and orange colors are successively used. Write the fringe width in increasing order. We have fringe width beta equal to d lambda by d, that you know. Here first green light is used, then yellow color is used, then orange color light is used. What happens if wavelength increases, color changes means wavelength changes. Wavelength changes, what happens to fringe width? Fringe width also changes, isn't it? So wavelength of which color compared to green, yellow and orange? We know wavelength of orange color is greater than wavelength of yellow, greater than wavelength of green. This is the order, isn't it? So wavelength of orange color is greater than wavelength of yellow light is greater than wavelength of green. So as wavelength increases, what happens to fringe width? Fringe width also increases. So beta corresponds to orange is greater than fringe width corresponds to yellow, greater than fringe width corresponds to green. Okay, so increase, we have to arrange fringe width in increasing order, no? So increasing order is fringe width of green less than fringe width of yellow less than fringe width of orange. Okay, so this is the increasing order of fringe width. Third question, in Young's double slit experiment, the slits are 0.2 mm apart and the screen is 1.5 meter away. It is observed that the distance between central bright fringe and the fourth dark fringe is 1.8 centimeter. Find the wavelength of light used. So what are the values given? The slits are 0.2 mm apart. The slits are 0.2 mm apart means that is represented by small d. 0.2 millimeter, we can convert to meter, 0.2 into 10 raised to minus 3 meter, that is given. And the screen is 1.5 meter. So screen is at a distance capital D. Capital D is 1.5 meter. It is observed that the distance between central bright fringe and the fourth dark fringe is 1.8 centimeter. We know the position of dark fringe. Position of dark fringe from the central maximum is 2n plus 1 into d lambda by 2d. That is the formula for position of dark fringes from the central maximum. Okay, so we have the formula y is equal to 2n plus 1 into d lambda by 2d. Okay, 2n plus 1 into d lambda by 2d. That is the position of all dark fringes from the central maximum. If you put n equal to 0, okay, n equal to 0, what is that? D lambda by 2d. So that is the position of the first dark fringe. Okay children, so just n equal to 0, put n equal to 0, y equal to d lambda by 2d, that is the position of first dark fringe. Put n equal to 1, y equal to what? 3d lambda by 2d, that is the position of second dark fringe. Put n equal to 2, y equal to 5d lambda by 2d, that is the position of third dark fringe. Here what is given? Here the position of the fourth dark fringe is given. That means we have to put n equal to 3. Okay children. So this is the original formula. N equal to 0 means that is the position of first dark fringe. N equal to 1 means that is the position of second dark fringe. So we have to take 1 less in the case of dark fringe. So in order to find the position of the fourth dark fringe, 1.8 centimeter means we have to put n equal to 3, isn't it? So put n equal to 3, y equal to what is the answer? 7d lambda by 2d, that is given as 1.8 centimeter. You can convert to meter. Okay, so we have the formula y equal to 2n plus 1 into d lambda by 2d. Here fourth dark fringe is given. Fourth dark fringe position is given. That means we have to put n equal to 3. So y equal to 7d lambda by 2d as 1.8 into 10 raised to minus 2 centimeter, 10 minus 2 meter. Now we have to find out lambda, no? Lambda equal to question mark. Capital D is known, small d is known. We can just substitute and we can find out the formula value of lambda. We can substitute lambda as 1.8 into 10 raised to minus 2 into 2 into d, 0.2 into 10 raised to minus 3 divided by 7 into capital D, which is 1.5 meter, and after simplification we will get the answer as 6.86 into 10 raised to minus 7 meter. So wavelength of light used is 6.86 into 10 raised to minus 7 meter. Okay children. Next question, two slits 0.125 millimeter apart are illuminated by light of wavelength 4500 angstrom. The screen is 1 meter away from the plane of the slits. Find the position of second bright fringe from the central maximum. Also find the separation between second bright fringes on both sides of the central maximum. Okay, so here what are the values given? Two slits 0.125 millimeter apart, that is small d. Small d is 0.125 millimeter, you can convert to meter. Then illuminated by light of wavelength 4500 angstrom. So wavelength is 4500 angstrom, that means 10 raised to minus 10 meter. Screen is 1 meter away. The position of the screen is represented by D, capital D, 1 meter. Find the position of second bright fringe from the central maximum. So position of bright fringes from the central maximum, we know y equal to dn lambda by d. Already in that derivation we have discussed. So position of bright fringes from the central maximum is y equal to dn lambda by d. So we have y equal to dn lambda by d. So this is the position of bright fringe. So here we have to find out the position of second bright fringe, that means y we have to find out. So put n equal to 0, that means y equal to 0, that means the position of the central maximum, central bright, central region is always bright. Now put n equal to 1, y equal to d lambda by d, that is the position of the first bright. Put n equal to 2, y equal to 2d lambda by d, that is the position of second bright fringe. So position of the second bright fringe, put n equal to 2. So y equal to 2d lambda by d. We have to find out y, no? So just substitute 2 into capital D is given, lambda is 4500 into 10 raised to minus 10 meter, divided small d is 0.125 into 10 raised to minus 3. And after simplification we will get the answer as 7.2 into 10 raised to minus 3 meter. So this is the position of second bright fringe, position of second bright fringe from the central maximum. So first part is over. Second one is also find the separation between second bright fringes on both sides. So we know that in indifference pattern, bright fringes are formed on both the sides. Okay, on both sides of the central maximum we can see the bright fringe. So position of the upper bright fringe is 7.2 into 10 raised to minus 3. Position of the lower bright fringe is also 7.2 into 10 raised to minus 3. Okay, so from the central bright fringe on the left side or right side, or on the top region or bottom region, we can find the second bright fringe. So what is the separation between two bright fringes on either side? That is given by, so separation between second bright fringes on either sides of the central maximum is 2 into 7.2 into 10 raised to minus 3, because on the both side of the central maximum we can find the second bright fringe. Okay, so the distance between two bright fringes on either side is 2 into 7.2 into 10 raised to minus 3, that is 14.4 into 10 raised to minus 3 meter. Okay children. What is the effect on the indifference fringes in Young's double slit experiment due to each of the following operations? The screen is moved away from the plane of the slits. Number 2, monochromatic source is replaced by another monochromatic source of shorter wavelength. Number 3, the separation between the two slits is increased. The width of the source slit is increased. Next one, the monochromatic source is replaced by source of white light. Then source slit is moved closer to the double slit. So if each of the following operation take place, what happens to the indifference fringes? What happens to indifference fringes means whether indifference fringe is formed. If formed, what is the width? What happens to the width of the fringe width of the indifference pattern? That's a question. Okay. So this is the experimental arrangement of Young's double slit experiment. Here this is the original source. In front of it a slit is placed. Then here two slits are placed. These two slits act as the coherent source, and the screen is placed some distance from the coherent source. Here the distance between double slit and the screen is capital D, and the distance between the two slits is small d. Clear? So this is capital D, and the distance between the current source, that is small d. We can do one by one. Number 1, the screen is moved away from the plane of the slits. Number 1, screen is moved away. The screen is moved away from the plane of the slits. What happens to fringe width? Okay, so first one, we have the fringe width is given by the formula. We have fringe width. Linear fringe width beta equal to d lambda by d. This is the formula for fringe width, isn't it? Now, number 1, the screen is moved away from the plane of the slit. Screen is moved away from the plane of the slit means capital D increases. Capital D increases. What happens to fringe width? Capital D increases means capital D increases. So fringe width also increases, isn't it? The second one, monochromatic source is replaced by another monochromatic source of shorter wavelength. That means here wavelength, here source is placed, its wavelength is decreased, shorter wavelength, lambda decreases. Shorter wavelength means lambda decreases. What happens to beta? According to the formula, lambda decreases, beta also decreases. Then number C, the separation between the two slits is increased. Separation between the two slits means small d is increased. Small d increases. What happens to beta? Small d increases, beta decreases. The next one, the width of the source slit is increased. This is the source slit. Okay, the width of the source slit. This represents the source slit. Its width is increased. So there is no direct relation between fringe width and the width of the source slit. Okay, there is no formula relating fringe width and the width of the source slit, but we have to check whether interference pattern is formed or not. So there is one condition for forming the interference pattern. The condition is, let the width of the source slit is represented by small x. This width is small x, and the distance between source slit and the double slit be capital X. Okay, so small x is the width of the source slit and capital X is the distance between source slit and the double slit. So let small x is the width of the source slit, capital X is the distance between source slit and the double slit. For clear interference pattern to be seen, the condition x by x, small x divided by capital X should be less than or equal to lambda by d. For clear interference pattern to be observed, this condition should be satisfied. Okay, small x means the width of the source slit, capital X means the distance between the source slit and the double slit. That should be less than or equal to lambda by d, and this condition is satisfied. That this condition should be satisfied. Okay, so now we can do the next one. The width of the source slit is increased. Width is increased, that means small x increases. Small x increases, again if this condition is satisfied, we will get the interference pattern. Okay, even if small x is increased, if the condition is satisfied, till the condition is satisfied, we will get the interference pattern, but there is no change in the fringe width, because fringe width does not depends on small x. Okay, so if small x increases, if the source slit, the width of the source slit is increased, we know x increases, small x increases. Again, if this condition is satisfied, we will obtain the interference pattern. Otherwise, if the condition is not satisfied, interference fringes disappear. Clear, children? So if the answer is width of the source slit is increased, still the condition is satisfied, we will get the interference pattern, but there is no change in the fringe width. After that, if this condition is not satisfied, interference pattern disappear. Okay. So if x increases, the interference pattern is obtained till the condition is satisfied. The fringe width remains same. If the condition is not satisfied, the fringes will disappear. Okay, children. Now the next one, F we can do first. Okay. The source slit is moved closer to the double slit. That is also related to the same answer. Source slit is moved closer to the double slit. Source slit is moved closer means here this slit is moved closer to the double slit. So capital X decreases. Source slit is moved closer to the double slit means capital X decreases, isn't it? Capital X decreases. Is it clear, children? Source slit is closer to the double slit means capital X decreases. Again, if capital X decreases, still the condition is satisfied. Okay, still the condition is satisfied, we will get the interference pattern with there is no change in the fringe width, but after that if the condition is not satisfied, the fringes will disappear. Same answer. Clear, children? So, if capital X decreases, again if the condition is satisfied, we will obtain the interference pattern with fringe width remains same, otherwise if the condition is not satisfied, the fringes will disappear. Here also the answer is same as the previous one. If capital X decreases, interference pattern is obtained till the condition is satisfied, the fringe width remains same. If the condition is not satisfied, the fringes will disappear. Okay. So, next part we can do the E part. The monochromatic source is replaced by white light. If monochromatic source is replaced by white light, we know that white light consists of 7 colors. So, center fringe, the path difference of the 7 colors at the center remains same. Phase difference also remains same. So, at the center white light is formed. Okay, all the colors combine at the center to form white light. So, center region is always white. On either side colored fringes are formed. Okay, and closer to the white center, central white, red color is formed and farthest will be blue. Okay, closer to the center region, red color is formed and the farthest will be blue. That means on either side of the center white colored fringes are formed. And after some point it will be fully illuminated. Clear, children? So, if monochromatic source is replaced by white light, center region is always white, on either side colored fringes are formed. So, this is what we see in colors in oil film, colors in soap bubbles, that is due to the same phenomenon. So, their light is sunlight or white light. So, colored fringes are formed. Okay, see the answer. The interference pattern will be colored. Center fringe is white and on either sides colored fringes are formed. The fringes closest on either side of the central right fringe will be red and the farthest will appear blue. After a few fringes, no clear fringe pattern is seen. So, fringes are formed, colored fringes are formed only closer to the center region, on either side fully illumination or no clear fringes are seen. Okay, children? Now, we move on to next question. In Young's double slit experiment, the width of fringes obtained with wavelength 6000 angstrom is 2 mm. Calculate the fringe width if the entire apparatus is immersed in a liquid of refractive index 1.33. So, in air, if it is used in air, wavelength of light is 6000 angstrom and its fringe width is 2 mm. If the whole apparatus is immersed in liquid, what happens to fringe width? That is the question. So, in air fringe width is 2 mm, in the medium of refractive index 1.3. So, 1.33 refractive index, it is water. Okay, if it is immersed in water, what happens to fringe width? That is the question. So, what are the values given? Original fringe width is 2 mm. Okay, in air the fringe width is 2 mm, that is 2 into 10 raised to minus 3 meter. Wavelength of light used is 6000 angstrom. So, that is 6000 into 10 raised to minus 10 meter. We have the formula for refractive index n equals wavelength of light in vacuum divided by wavelength of light in medium. We have the formula for refractive index of any medium is wavelength of light in vacuum divided by wavelength of light in medium. So, we can write lambda divided by lambda dash. Okay, so this is a general formula. Now, we have the fringe width of fringes in air. In air, fringe width is given by the formula d lambda divided by d. In medium, fringe width is given by, let it be beta dash. Beta dash is equal to d lambda dash divided by t. So, fringe width in air is given by beta equal to d lambda by d. In medium, it is given by d lambda dash by d. What is lambda dash? Lambda dash can be written as lambda by n, no? So, lambda dash using the formula n equal to lambda by lambda dash. So, what is lambda dash? Lambda divided by n. So, we can write d lambda divided by n into small t. Clear? So, we have to find out beta dash, that is the question. Beta dash is equal to question mark. So, beta dash is equal to, beta dash means fringe width in the particular medium, that is water, is d lambda dash divided by lambda, d lambda dash divided by d, and lambda dash is, what is lambda dash? Lambda by n. We can just substitute. Equal to, what is d lambda by d? D lambda by d is beta. So it is beta by n. Beta, what is the fringe width? 2 into 10 raised to minus 3 divided by n. What is the refractive index of the medium given? 1.33. So fringe width in the particular medium is 2 into 10 raised to minus 3 divided by 1.33, and the answer is 1.5 into 10 raised to minus 3 meter, or 1.5 millimeter. So we can say that the fringe width decreases. So in air the fringe width is given, in media how will you find out the fringe width? That original fringe width divided by the refractive index. So the general formula is, in any medium fringe width is given by original fringe width in air divided by the refractive index of the particular medium. So in air the fringe width is given, in medium the fringe width always decreases by how much times? The refractive index time.